Welcome to the first lecture of part 7. In this lecture, we're going to talk about count data, and we're going to explore the use of Poisson regression in order to model count data. The Poisson distribution describes the probability that a random event will occur in a time or space interval when the probability of the event occurring is very small, but the number of trials is very large. So the assumptions in limit of the binomial process will be that the probability is approaching 0, the number of trials is approaching infinity, and the product of the number of trials and the probability is your mean mu. So when dealing with count data where the probability of occurrence within a time interval is very small and the number of trials within that time interval is very high, you can imagine that when you look at the frequency distribution, for instance, when you have on your x-axis the number of occurrences per time interval going from left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you can imagine that most of the frequency is going to be in the 1 or 2 or maybe 3 occurrences per interval, and then you have this very long tail to the right where the increasing number of occurrences per time interval, so let's say 4, 5, 6, 7, 8, 9, 10, is going to slowly diminish in frequency. So this is what you're looking at when you're dealing with count data. Now, of course, you would like to model this and predict that count or that rate, because now that it's a number of occurrences per unit time, that's a rate. We can use what's called the Poisson regression, and luckily the Poisson regression is part of the generalized linear models, which we've seen in the previous parts of this course. Now, of course, it takes advantage of the Poisson distribution function. And the link function that we're going to use is the log, which is what's commonly used. I've just put down here on the slide the Poisson probability distribution, and x is a random variable, and lambda is your rate. So the Poisson response variable may simply be modeled as the rate, which is what you're interested in, so mu, and the other side of the equation, which we've seen before in the logistic regression, for example, you have to exponentiate the linear portion of your equation, right, which you've seen before. Beta naught being your intercept and beta 1 x1 being your first covariate. Now, sometimes the count responses will pertain to unequal units of time or space, and you'll see, unfortunately, this happens quite frequently. And in such a case, then we can't use just mu because we have to adjust for the various different time units. And so we just divide by t within your unit, time t within your unit, and that's when we get lambda, your rate. Now, in SAS, in the coding, you would use the offset function, option of log of t, your time t. And so then your Poisson regression equation will look like the one on the bottom of this slide, where you are now using the rate adjusted for the unequal units of time or space. So now when we throw in the log link, we simply just take the log of both sides of the equation, and now the log of the rate is now going to be equal to the log of the exponentiated linear portion of your equation, which, of course, you're left with simply the linear portion of your equation. So now we have, or we can perform, linear regression. So every time we want to apply a model to our data, we always have to be very careful that the model fits the data well, because if it does not, then our estimates are going to be much farther from the truth, and therefore we have a poor model. So when you're dealing with count data, and in this case the Poisson distribution, you're dealing with over-dispersion, which means that your model does not fit the Poisson distribution. And one of the characteristics of the Poisson distribution is that its mean is equal to its variance. So if we see that the observed variance is greater than the mean, and this is known as over-dispersion, it tells us that the model is not appropriate. And this is a common reason for the exclusion of relevant explanatory variables. So this is what you're going to look for when you're adding your explanatory variables to the model, and you need to see if the model fits, if it's a good fit, is you're going to check over dispersion. So let's jump into a SAS example using Poisson regression. So our outcome is going to be the number of patient visits to a medical clinic. And our predictors, or explanatory variables, are going to be, first, the number of nearby housing units. So how densely populated is the area around the clinic. The average household income. The age of the housing units, so meaning how old are the housing units. The distance of the nearest competing clinic. And the distance of the clinic to the nearby housing units. Here's the code to load up your data in SAS. Now this, of course, is nothing new to you guys. You are all experts now. Here's the code for running your Poisson regression, and I'm only going to go over it just quickly. So proc genmod is going to be the procedure in SAS that you use in order to perform Poisson regression. And you'll see that how you set it up is very similar to what we've done in the past with procglm and proclogistic. So you have your model statement here, and this looks very similar. You have your outcome and all of your explanatory variables. We're going to define the distribution, which is Poisson, and the link, we're going to say log. This out here for the output, and here your mu hat for I, and your residual deviance, we're going to call devi, and we're going to use these in order to calculate the deviance. This is just to print some of your data and have a peek, and this is just a temporary data set in order to be able to do the calculations for your deviance. And then we're going to plot, once we've calculated, well, SAS calculates it for us, we're going to plot our deviance so that we have a nice visual of whether or not we have over dispersion. All right, so what do we get when we run this code? First and foremost, we just confirm the model information. We're using Poisson with a log link. Perfect. We have 110 observations. That's always a good thing to check. Here, first and foremost, right up here is your deviance and your scaled deviance. I'm not going to go into detail, but your deviance is what you're looking for. And in general, you would like your deviance, a perfect deviance would be 1. And anything when you stray larger than 1, then that you're slowly getting over dispersion. For instance, if you had 10, that would be bad. You were like, whoa, that's definitely not a good model. Okay. When we look down here, first algorithm converge, that's always a good sign. When you look at your output down here for the analysis of maximum likelihood parameter estimates, here you find your parameter estimates. And I've just picked one out as an example, and it's the distance of the clinic to your housing units. And you'll see here that the estimate is negative. It's a negative 0.1288. And you'll remember that you need to exponentiate this in order to get the value in the units you're expecting, which in this case is going to be 0.879, and your outcome is number of patients. So the 0.879 would be in patients. So how do you interpret this finding? So if we want to interpret it as, from the parameter point of view, the estimate of your parameter, if the distance from the clinic was to increase by 1 kilometer, the difference in the logs of expected counts of patients visiting the clinic would decrease by 0.1288. while holding all other variables in the model constant, of course. If you want to, express this finding in the units of interest of your dependent variable, which is patients, you can say if the distance from the clinic were to increase by 1 kilometer, the number of patients visiting the clinic would decrease by about 1 patient while holding all other variables in the model constant. So this is how you perform Poisson regression with count data. I'm just giving you a little taste of this because there's inevitably a lot more to this when you get into a full involved analysis. But this at least gives you an idea, and it just reinforces what we've been teaching about this whole general linear model, that I don't want you guys to remember recipes. I want you to remember the concept of the general linear model and how you apply it, because then if you forget some of the details, that's okay. You can just ask someone to help you to do that. But most importantly is you remember the statistical concept. Okay. Let's calculate the deviance. Now, here's just a hand calculation as an example. Not asking you to do that in any way. As you can see here, there's an example of 10 that SAS did for you. If you wish to calculate the first observation, it's right here, okay, and it just shows you that we get the same answer. And this is a similar equation that we use in the logistic regression as well. So let's plot them. This is the plot of your deviance, and what this allows you to do is to visualize how your deviance or your residuals are in your data set. And this will give you an appreciation, a quick visual appreciation of whether or not your model fits. Now you'll remember that we, in the 2 slides ago, we saw that deviance was only just a pinch over 1, and so this is looking good. So the other thing you're going to look at in this plot is whether or not it's consistent, because you'll remember that your residuals need to be appropriately distributed in order to meet the assumptions. So in this case, it looks like there's no bias or skewedness in the residuals, as well as the deviance being low. We can say, oh, this is a good model. And this brings us to the end of Lecture 1, Part 7, and actually to the end of our 6-week Biostatistics crash course. Now, what I recommend is you take the time to review the video lectures again in order to just try and grasp a little more from the slides going through it, because the first time you go through, it's a little overwhelming, and you are, of course, learning and picking stuff up, but you may miss stuff. And so when you listen to it again, you're going to be able to pick up those details and actually further your knowledge and confidence in biostatistics. Thank you very much for listening, and hopefully we'll see you in another course.